Muy buenas tardes a todos. Vamos a comenzar con la presentación pública de tesis de maestría del estudiante Ángel Martínez y Fuentes de la Maestría en Ciencias Astronómicas. El título de la tesis es On the Generation of Subphotospheric Acoustic Sources. El director de la tesis es el profesor Benjamín Calvo de su Fundación Internacional y el coeditor es el profesor Juan Carlos Martínez. Los jurados son los profesores Dominic Bux, del Instituto de Física de la Universidad Subphotospheric de la República Checa, y el profesor Santiago Vargas Domínguez, del Observatorio Internacional. Entonces, antes de la presentación, tiene 45 minutos. Veremos cuando parten. Aquí está.
So, good afternoon, everyone. My name is Daniel Martínez y Fuentes. I am Master of Student in Astronomy here at National University of Colombia. Today, I'm going to be presenting you for this work, this thesis, which is called On the Generation of Subphotospheric Acoustic Sources. My supervisor is Professor Benjamín Calvo, and my advisor is Dr. Juan Carlos Martínez at Space Sciences Laboratory, University of California, Berkeley. Okay, so let's start with a little introduction. Hydroseismology is this branch of solar astrophysics which helps us to understand solar interior conditions and properties. This is done by measuring oscillations happening at the solar surface. The image at the bottom here shows traces of a certain kind of waves which have this property that as they travel to greater depths in the solar interior, since there is an increase in the sound speed value, they refract back to the surface. When they hit the surface, we analyze those disturbances and study these interior conditions. How do we measure those oscillations? We make use of images from the Hydrodynamic and Magnetic imager, the HMI instrument, on board this satellite, the Solar Dynamics Observatory, which is shown here at the left. HMI takes images of the sun around the absorption line of iron 1 at 6,173 angstroms. It consists of 6 filters from where images of the sun are taken from, for each one of the circular polarization states to the left and to the right. So we have 12 filtrograms, which, after plugging them in an algorithm, we get these 3 main observables. They continue intensity. We often refer as these line of sight velocity maps as Dopplergrams, and are the one we use to study those oscillations in the sources. A very interesting phenomenon regarding the propagation of these waves are seen as Sustentación events. These are seen as propagating waves traveling radially outward from a given source that you can see here in this movie. This movie was actually made by taking consecutive images in the Dopplergrams to get these images where the Sustentación event is related to this expanding wave here. They follow up the same propagation rules as these waves traveling in the sun, being bent back, refracted back to the surface. All right, what is the trigger of a Sustentación event? There are some hypotheses regarding the generation of these Sustentación events. The first are related to the magnetic field, where there are Lorentz force on the solar surface, generating those events here in traveling as these waves. The other hypothesis is related to atmospheric events in which there are changes in pressure and temperature, generating, for example, pressure shocks, having an impact on the solar surface, generating those Sustentación events. We have two main techniques to observe these Sustentations. One related to the time distance diagrams, and the other one to hydroseismic acousticography. With time distance diagrams, we calculate angular averages in a certain region where the Sustentación is believed to be propagating. And for each one of those averages, the value is plotted here in this diagram for each frame. So we have a diagram such like that, in which the presence of the scientific event is related to this ripple as shown here by this white arrow. We can even overflow the theoretical path of these waves as shown here by this thick red line, which is called the Ratepath Approximation. On the other hand, seismic acoustic holography is this computational technique intended for the reconstruction of the acoustic field in the solar interior by measuring those surface disturbances. The main idea of this technique is to render images of the sources that give rise to those surface disturbances. In the image at the left, we see here an idealized example where we have two seismic sources embedded in the sun, different depths. Each one of these sources propagate waves in all directions, hitting the entire sun, and eventually part of these wavefronts are seen in the surface as expanding ripples traveling in the sun's surface. By making calculations with acoustic holography, I'm going to be using holographic technique, acoustic holography. It's the same for this purpose. By performing holographic calculations of the acoustic field, this can be performed at several depths in the interior of the sun. For example, if we calculate the acoustic field at a depth where the first shallower source is located, then we have a diffraction limited image of this source as seen here by this plot on the right. In contrast, if the source is located far below or above this sampling surface, notice that the signature does not disappear, but rather is a little bit focused from this original shape. There is an advantage of this technique related to the strong parallels there are with optic electromagnetics, with geometric optics. In which, for example, we can account for this light for this seismic source to be like a light source where light rays travel in straight lines through an uniform medium, and after the action of this lens, we have on the screen an image of that source. Here in the analog, we have that these wavefronts coming out from this seismic source travel following these propagation rules as for this acoustic interior. Eventually, these wavefronts arrive to the surface in a range of radii. This range of radii is where we make those holographic calculations to render the acoustic field. For example, well, as you can see here, there is the pupil of observation, where is encompassing this range of radii on the surface. So, a pupil of observation is something like that. The authors of this technique provide this example in which they locate two alphanumeric characters located at different depths in the solar interior. The first alphanumeric character is located just beneath the solar surface, and the other one is located at a depth of 56 megameters in the solar interior. They provide these maps, which are called acoustic power source density maps, which are the acoustic field at each one of these depths. As the depth increases by applying this holographic technique, we see that there is a blurring of the first alphanumeric character as this depth increases. Whereas for the second one, we have that the second alphanumeric character is focusing up to this shortly signature at 56 millimeters. The overall objective of this thesis is to study the possible mechanisms of generation of these acoustic signatures at different depths in the solar interior. In order to achieve this, we select these specific objectives, which were characterize solar seismic events at different depths and frequencies. Also analyze the possible thermodynamic anisotropies, as well as the magnetic field for each source. All right, in order to do that, we select 5 solar polar events which were known to be hosting a suncritic event. In other words, they were seismically active. These were also selected in order that they were in regions near the solar center and not in the limb because of projection issues regarding this holographic technique. All right, let's have a look at the results. The first solar flare we analyzed was an M9.3 class solar flare event hosted by active region 11621, happening on July 3rd, 2011. This slide shows the image of such solar flare event in, for example, the AI channel at 151 angstroms, showing decreasing brightness of this energy release for this solar flare. The middle image shows the location of this active region with respect to the solar disk center. Here, the image on the right shows a zoomed view of this field of view region with a proper projection. All right, the first result we got was published as a paper in the Astrophysical Journal Letters with the title Ultra-Impulsive Solar Flare Seismology. Here, this paper was published back in 2020, actually 1 year before the thesis submission. In this work, we analyzed images of the acoustic field at different frequencies in the solar surface. It was performed by calculating the holography with this pupil of observation within a radius of 7 megameters and an outer radius of 84 megameters. The images here at the right show for the planet A a continuum intensity image where we overflow this white light excess, which is actually the case in order to provide a better visual contrast of the location of this white light feature in this active region. Succeeding images from panels B, C, and D show the source density maps calculated at different passbands between 5 to 7 millihertz, between 7 to 9, and between 9 to 11 millihertz. As the frequency increases, there is a sharpening in the features located here in these maps. Previous studies have shown that for between the range from 7 to between 5 to 7 millihertz, if we calculate the energy distribution of these solar of these active sources, the greatest energy is released in that range, around 6 millihertz. However, we detect for our solar flare event that there was a component extending well beyond these 6 millihertz. It's actually an ultra-impulsive component, showing there are features seen at this specific bandpass. This brings a lot of good prospects regarding the study of these sources, because now we have a diffraction limit of about 760 kilometers, which in area with this pupil is 3 times better what we have by analyzing these seismic features between 5 to 7 millihertz. However, we are spectrally limited because, well, the HMI takes images of the sun every 45 seconds. So we have a sampling rate, and thus we are left with an upper limit of the frequency in which we can reconstruct our images, which is given. This is given by the Nyquist frequency, and is given by this value by this expression for HMI is 11.1 millihertz. So we don't go further with the analysis, extending these frequencies of 11 millihertz. As you can see in this elliptical region here, there are 2 features related to those concrete transients in this region of the sun. Let's have a look at this. Let's set a field of view in which we put our images. This field of view is represented here in the panel B as the source density map. We notice there are 2 sources, which we call source B and source A. And it's actually interesting because source A is seen to be bifurcated into 2 kernels, which we know, but kernel A southeast and kernel A northwest. Next, we overflow the contours of each one of these sources into other observables. For example, in the continuum intensity image, we see the first source A, is located in a penumbral part of this active region, whereas source B is located in a boundary of this umbral region. Now, by analyzing this over the line of sight magnetic field, we find that source A is set where the magnetic field has a boundary where this value increases from 90 Gauss and 900 Gauss to 1150 Gauss. That is remarkable because there is an increase of about 250 Gauss for this region. So it is like this magnetic structure has some sort of relationship between the dynamics or even generation of these sources. Panel B shows the local acoustic powers of Doppler disturbances in which we see for this source B to have Doppler signature exists, but it's a void here for this source A. Now, those contours over the Doppler randoms shows this set of images. Panel A is the raw image from this Doppler random, in which we see the location of these sources. Succeeding panels B, C, and D show transient images, that is the raw Doppler subtracted by the raw pre-Fuller Doppler, and this is done so as to have a better visualization of features happening as a function of time for these maps. For example, in the panel C, source A, the bifurcated one, is seen to have a red shift, where the source B seems to have a blue shift. What is noticeable here is the location of the strongest Doppler signature, the strongest Doppler depth transient, which is marked by the location of this arrow. Some authors proposed these regions where these Doppler features are seen to be the location of the actual sources generating those Stumpf events. However, we see that for this region, where the strongest Doppler transients are, it is actually the void of any acoustic anomalies in any of the passbands. Let's see the temporal progression of these kernels. So here we see that the kernel A northwest leads the kernel A southeast by approximately 200 seconds. So it is like has some sort of casual relationship between the generation of these between one kernel to another. In contrast, the source B fits in halfway between these two kernels. So we take into account these difference in time in a few more slides. The second result we got was also published as a paper in the Astrophysical Journal Letters with the title Submerged Sources of Acoustic Transient Emission from Solar Flares, also published back in 2020. In this work, we analyzed these acoustic field maps at different depths in the solar interior. The movie here shows a truly amazing thing happening here, that is, we have a very focused image of one of the kernels embedded in the solar interior. So we have the source density map, which is the one I previously have shown you. And if we select a field view related only to these kernels from the composite source, by applying this holographic technique, we find the sequence of images. Here, well, we find that this southeastern kernel is seen to be better focused at a depth of approximately 1 megameter before beneath it by its sun. Whereas, for example, is becoming the predominant feature here at 840 kilometers. So it is like we have two seismic transients located beneath the solar structure, one located just beneath the solar surface and the other one located at a depth, at a greater depth. So the hypothesis here is that the morphology of these sources is related not only to a strong compaction of these sources in the solar interior, but also related to the energy source that is feeding these acoustic transients. We do not say that these submerged acoustic transients are independent from the solar flare event. Actually, what we propose here is that the flare is part of the solar flare traveling downwards. It has some disturbance in the interior, triggering those events. So this flaring part of the solar flare triggers first the shallower source and then the deeper source. But in order to do the math of this, we make a simple model in which we consider these two sources to be located in two different finishes in the solar interior. So we calculate the depths of these two emitters in order to fit those observations. We found that the shallower source is located at a depth of 200 kilometers emitted by sun, and the deeper source is located at a depth of 1,150 kilometers. So it secures then a causal relationship between the first shallower source and the deeper source. So we can calculate the trigger speed of these events. The trigger speed regarding the distance between these kernels and the temporal evolution of these two gives us that the trigger velocity is around 4.75 kilometers. So let's have a look at the nature of this speed. By making a calculation of the sound speed value in this range, taking a mean of these sound speed values, we have that has a speed of 10.7 kilometers per second, which is actually twice the trigger speed we found for these events. On the other hand, the alternative speed can be set so that this velocity is actually the trigger speed. That constrains the magnetic field to have certain values as a function of depth in the solar interior. And for example, at a depth where the deeper source is located, we have a magnetic field of about 3,000 Gauss value. We now ask, where does the energy come from? But before the release of energy of the solar flare event, there's magnetic energy stored in order to be converted to thermal and kinetic energy. In the neighborhood of these sources, in the solar structure, there are also magnetic forces, magnetic fields in this overall region. So also these loops extend to greater depths in solar interior. So it's like there could be some energy, some magnetic energy stored in the solar interior, and after some stabilization in, for example, the structure of the subsurface region, there is a conversion between this magnetic energy into acoustic energy, which we have to see at these propagating events. This is strongly favored if the beta parameter of plasma is around the unit, which is held by this constraint of the magnetic field, for example, in this depth. Well, the source, again, we analyzed was this widely analyzed X2.2 class solar flare event. Here in this screen, in this slide are the images of the field and intensity for this active region of over the solar surface. So here in this slide, I'm showing you the values of these maps, of these acoustic maps, calculated around 3 millihertz and 6 millihertz. This was a study from Alvarado. This bottom row shows the images calculated around 7 millihertz and 10 millihertz from Sharkov et al. We calculated also these between 9 to 11 millihertz. We find this conspicuous component there, ultra-impulsive component. And by making also estimations of the acoustic field as a function of depth As you can see in this sequence of images, we can also say that part of this acoustic transient is submerged into the solar interior. And now the three other solar flood events we analyzed are shown here. They were located in the same active region. And the something events they hosted, we can detect them through these source acoustic density maps around 10 millihertz. We notice there are components for each one of these something events. And also, making a depth diagnostics, we find there are some features embedded in the solar interior. For example, for the M1.3 class solar flare, we find there are also components which are seen at certain depths which aren't seen in solar surface. So to test whether a magnetic perturbation in the solar interior can give rise to those acoustic signatures, we provide a numerical simulation. For this purpose, we use Pluto, a numerical code for computational astrophysics, in which we solve this conservative equation, and it's intended to solve high Mach problems in compressible dynamics. Here we make use of the Magneto Hydrodynamic Non-Relativistic module. In this module, the equation becomes the set of equations related to mass conservation, Newton's second law of movement, the Faraday's equation, and the energy conservation. We make use of these approximations in order for this scheme to be easier to solve, such as the Ampere's law, the perfect conductivity limit without any viscosity, and an ideal gas approximation. What we want to do here is just fill the solar interior with model, in this case, the solar standard model. In this model, we locate a magnetic flux tube in this region, so we have to properly set this magnetic field. The exterior of this tube is filled with these values as given by the solar standard model, and the interior of the magnetic flux is actually placed in magnetic field with constant cross section axis with an axis symmetry. This follows the review of Martínez et al. Here, we consider the interior of the magnetic flux tube to be devoid of any acceleration terms, so we have a magnetic hydrostatic model. In this model, we select a view of this magnetic field, horizontally and vertically speaking, as these functions, which are so similar fields for the magnetic field. Plugging in those components into this hydrostatic model, we get the horizontal component to be related to this lateral pressure balance between the interior of the magnetic field and the exterior of it. And also the vertical component relates to the gravity that the magnetic flux is being weathered. So we select a proper profile of these, both the density and the pressure, so that the density and the pressure have a constant value through the cross section, and in regions near the boundary, it has a smooth change in order to be connected then with the exterior, which is given by the solar standard model. For the magnetic field, something similar happens. So in this case, we have a magnetic field value, which is constant across the cross section. And then in the boundaries, it shows this smooth curve to be zero in the external region of the magnetic field. We can play around with this factor here, with this variable, with this S variable, which tells us about the strength of the magnetic field as a function of depth. Here, for example, this plot shows two values for this S variable, in which we select which one of the magnetic field variations as a function of depth we want to simulate. Now, in the results of this part, we set a simulation box with 300 pixel, with a resolution of 300 pixels in each one of these directions. That gives us a resolution in the x direction, horizontally, of 53 kilometers per pixel, and in the vertical direction, a resolution of 31.3 kilometers per pixel. These images here show the variation, how these variables change as a function of depth in the solar interior. In order to provide a better stabilization of this code, we provide what we call wave absorbers, upper and lower boundary conditions. These are set in order for, well, at the beginning of the code, there are several waves filling the entire solar interior. And so there are reflections happening at these lower and upper boundaries. So in order to avoid that, we use these wave absorbers, in which those waves which travel through these layers are absorbed in that region, preventing those bad reflections. Well, the lateral boundary conditions are set normally as optimal conditions for this one here. In the simulation, in the stabilization process, we set the perturbations after 1 hour of this runtime. That is because after 1 hour, we have a very best view of the stabilization of these variables here. For example, in this movie, I'm showing you these variables: the pressure, density, and the velocity. And we see that after 1 hour of this simulation, the field stabilizes, so we can actually there make our simulations. To test the validity of the simulation, we provide a pressure perturbation related to these usual sample events. We make perturbations in pressure, as shown here by these two arrows in the top row. And after some time, we see wavefronts traveling in all directions in the solar interior. So we can calculate time distance diagrams, as for example this one, in which the first ripple shows the propagation of the sample event. And we can overflow this Ratepath approximation in here. Now, the magnetic field perturbation is related to, we have a certain region in the magnetic field, and we make a perturbation with a certain strength. Some minutes after this perturbation, we see in images of the velocity in the vertical direction, different images in the vertical direction, that there are wavefronts traveling in principally all regions of the sun, but we perceive them better in that region. Another perturbation gives us these wavefronts, which well, are better seen if we provide these time distance diagrams again, or these time distance diagrams. We see also we have something like events traveling as these waves that eventually are accelerating in the solar surface. Finally, we make a three-dimensional simulation using the new simulation box of with the Earth direction to be with this resolution, 93 kilometers per pixel, the angular direction with a resolution of 7.5 degrees per pixel, and the vertical direction with this new resolution. This takes more time to give us images, so we use this green average technique in which variables near the R=0 value are averaged in order to speed up calculations. Also, for the upper and lower boundary conditions, these walls will provide these wave absorbers conditions. The top row shows two images in which we, well, here in the first image, there is the density. The second image is the consecutive difference of these density, showing us there are flows in and out this magnetic field. We should take this into account in order to not confuse them with the actual syncretic event we might see with our perturbations. This in the top bottom shows the vertical profile. The vertical profile in which we make a perturbation, and after this perturbation, sometime after this perturbation, we start to see waves traveling, expanding rapidly upward from a given location in the solar surface. And this location from which these waves are traveling is marked by the projection of this perturbation into the solar surface. So we see this something like wave events traveling in the solar surface. All right, so this work we propose a mechanism in the solar interior closely related to the storage of magnetic energy for these acoustic events. Also, second conclusion we arrived was that observations at these high frequencies, or impulsive observations, ensures a better spatial resolution to make a better discrimination of features of these sources in certain depths in the solar interior. Also, for these events, we detect there are several layers where we find these seismic transits to be located at. And in fact, for one of those, we found these, there were two seismic transits located in the solar interior. And finally, we provide, in order to test the magnetic conversion into acoustic, a two-dimensional and three-dimensional Hydrodynamic simulation, which, as we saw, we can see these wave events traveling from this magnetic perturbation. All right, thank you very much.
Gracias. Entonces, ahora procedemos con la segunda parte de la presentación y responder las preguntas por parte de los jurados. Así que le doy la palabra al profesor Dominique.
Gracias. First of all, I want to say super presentation. Very, very nice. Especially I like the idea of having observations of phenomena and then trying to explain it and to further investigate it by simulations and figuring out what causes the phenomena. So in this sense, really nicely done work. I like it because it's from several aspects and so on. Unfortunately, I'm not the super expert in video seismology, so maybe my questions will be a little bit naive, or I'm not sure. We can start with the first one. You said in the beginning that you trace the waves, they go inside, and then they are refracted and come back to the surface.
Yes,
like in the quake, in the house quake from the flare. So I wonder why it cannot be just a surface wave? Like you initiate on the surface a wave and then it's traveling on the surface. So how can you differentiate between a full like surface wave and like a wave going inside the interior and coming back and causing then the ripples by being a refracted wave?
Okay, well, what we want to study here is the deepest structure of the sun. So by making theory of stellar oscillations, we find there are waves that travel following these paths as like following these skips in the solar surface. And actually, we saw those oscillations happening in the sun. For example, there's a well-known 5-minute oscillations associated to the sun, and it's related to these waves traveling. I know there are waves traveling horizontally, but when we do not analyze those waves here. To distinguish the propagation of these waves, for example, we measure the ripples on the surface, and through this theory of stellar perturbations, we can provide, for example, time distance diagrams showing the propagation of these waves traveling to the regions of the sun being bent back to the surface, being refracted back. For example, in here, where as for example in here, where this theoretical path is given by this, which is called the Ratepath Approximation, and it's related to these waves traveling deep in the sun and being refracted back. And so, by measuring those disturbances in the surface, we account that they are these type of
So practically, easily speaking, the velocity of the propagation is a different one. I guess if it's a surface wave, what is the internal temperature?
Yes.
Different, you showed a very nice method of the focusing, defocusing, where you get I guess it's assumed that the signal is then coming only from one layer. So practically you have your surface signal, and then you assume if all the signal would come from depth 0, then the source region would look like this. If everything comes from the depth 5.6 megameter, then you need this kind of source.
Yes. Well, actually,
so there is not like a unique solution. So it's like you need to know what you're looking for, and you say you look for the most focused thing.
right.
So like in this example, we know that we put the letter Soho, and then we look where does it look most like Soho, and that's our depth. But practically the solution from 11 megameters would also fit to what we see on the surface.
Yes, that's right. Because from these parallels, from these plots here, we see the calculating the acoustic field at a certain depth. For example, if this source is located at different location with respect to this sampling depth, the image here is out of focus.
But I mean, so you still need the human interpreter to say, for example, that the more focused source is the more realistic one, and what we expect than the distributed one, because it could be in theory also a distributed.
Yes, that's right. In fact, also in these papers from these authors, they also gauge how, for example, an absorber would like a different depth, just placing the absorber at a certain depth. So by making calculations of this holographic technique, they say, okay, here we see that there are images, as for example here, of this first word, Soho, but it's not really there, because we know the more focused image is right there. It's some sort of a gauge for this.
But you showed us in a very nice example of the real observations, but you had the source in 2 different depths.
Yes.
But this means that practically there's an overlay. I mean, from the source in the one depth, it influences the interpretation of the source in the other depth. So can one try to disentangle it, like then to make the image out of 2 sources placed at the same time in different? Because I guess this is still like all the source is in 2,100 kilometer, all the sources in 0 kilometer. So can one improve the technique and like make it merging like multiple sources at the same time?
Yes, but in fact,
or maybe I misunderstood it.
No. What we have done here is just make a simple model in which, since we observe from this focus, the focus technique, that there are 2 sources embedded in the solar interior, one shallower and the other deeper depths in the solar interior. So we just make a simple model in which we consider the sources to be located in just thin sheets in planes in the solar interior. And by adjusting the depths of these emitters of this model, we can feed the observations. If we can feed the observations, then we say, okay, we can account for these waves to be located in 2 depths. But it's more like there is a vertical extension of these.
But sources. You think it would be worth to think about extending the method to like distributed sources, or
I think
or it's quite complicated?
Well, maybe a little bit more complicated. You just use this simple model of these emitters.
And then I have to practically, because I think in one example you showed the pupil space and you took like the first distance rho and the total distance where you consider others. So how do you estimate these ranges?
Sorry, which frame?
I think from the pupil where you consider the waves, there was one slide. You show some
These people or the
exactly this, for example. So how do you estimate how large the pupil? Because I guess the results depend if you take it narrower, if you increase it. So
yes, for example, if we want to make a depth diagnostics of these wavefronts in solar interior, then since this signature is a certain depth in solar interior, then you have waves that travel more deep in the sun and refract back to greater
so
radius.
practically the depth gives you then the ranges you need to consider. So automatically when you look in a different depth, you adjust the pupil.
Yes, in fact, for example, the inner pupil of observation here should be greater than the depth of the signal source.
But that leads me to the next question. I wonder about the co-temporality, because I guess you take the information at one time, but obviously if the wave has a longer travel distance, it needs longer time. So like what is closer to the surface source, or where you think like the surface point, it is like earlier in time than what is further away. Is this a problem? Because I guess the source is like evolving in time. So maybe if at one time you take the surface and close to the emission, like the information is kind of a different information than the one further away. Is this making any problems, or?
We measure the peaks of these waves. For example, in this terminal progression, we start to see these waves, and they have variation as a function of time. So we take the peaks of these temporal progressions in order to estimate the time difference between the appearance of the first and the second source.
Okay. And anything. So did you also look? Yes, because we have the time range. How quickly are the source regions evolving, changing? Is there any problem with the method, or? I mean, the method is so robust that what would be the temporal resolution it would go down? Like, because these events are happening really quickly. Yeah?
Oh yes, in fact, there is a temporal resolution as given by, because we are analyzing those images in bandwidths of 2 millihertz. So we have a temporal resolution of 5,000 seconds, 500 seconds. But here, we just analyze those peaks happening there, because if these sources are happening really quickly, then we wouldn't be able to properly look at them with this temporal resolution. But we analyze the curve that these peaks make as a function of time in order to see, okay, these peak happen in peak in certain time, and the other one happen in another time.
Okay. Very nice. And for the second part, because now I think this was the analysis of the flare of cosmic waves, and then you showed in the simulations how or what could be possible trigger causing the acoustic stuff. And you have this nice model of the vertical flux tube, and I think I sent you in my comments. I was wondering what happens with the magnetic fields, because we all know that the flux needs to be conserved if this divergence is zero. So practically, if the vertical flux becomes less, then we should get horizontal fields. So, because I never saw the horizontal field.
Yeah,
exactly. Like here in the VZ plots, we see the magnetic field is very strong at 6 megameters below the surface, I guess, and then it gets weak to the surface, of course.
yes.
But what happens with the magnetic field? Because it cannot just disappear.
We consider this a simple model of the magnetic field. We know there is magnetic flux conservation through these through the cross section of the magnetic field, but we just consider for the stabilization of the curve a simple, very simple model in which we set these magnetic flux curves to be constant cross section in order to perhaps avoid, for example, fluxes coming out from the gravity that this box feels. So we just say, okay, this is the simplest model we can think of. Just apply the model.
Because normally the flux tube should expand.
Yes,
the gas pressure is decreasing outside.
Yes, in fact, in the second part of the observation and analysis, the magnetic field, the atom velocity is set so that it accounts for the trigger velocity. And that means that the magnetic field should be squeezed as a function of time, as we
but like in this case now, in that sense, you violate probably then the direction speed criteria for the flux. Okay, just for the clarification. And then practically we see in your simulations like a conversion, also kind of a Magneto hydrodynamic waves. I mean, like we have the magnetic field into acoustic waves. Did you ever consider also to study the opposite, like the conversion of acoustic waves into MHD waves? Because I think this is like a hot topic for this corona leaking, how to get the higher atmospheric, and we have all these P modes and other acoustic oscillations, as you said, in the sun. So practically, if you have these flux tubes, then the impacting acoustic waves could cause magneto-acoustic waves traveling up the flux tubes. And
we didn't analyze that case, but there are papers in which they analyze for example, in sunspots, there is, for example, if we have P-mode waves, there is an absorption of these P-mode waves in the sunspot. And some of these authors may account for this absorption to be like a conversion between these acoustic modes to hydrodynamic.
Because I think this is really exciting topic, because it's this ongoing debate how we heat the upper atmosphere, and the question is how we get, for example, the acoustic flux in the higher atmosphere. Because normal acoustic waves, it seems, cannot penetrate; they are reflected and absorbed in the lower atmosphere, and so the people come up with these MHD waves. So of course, a conversion from acoustic flux into MHD would be very interesting. I have another question. You showed in very nice plots about the waves, the disturbances, the pressure in these simulated flux tubes, a little bit further, but one more maybe? One more, sorry. Yeah, these ones. I wonder what are the amplitudes of these waves, but of course it's very different if you have a strong amplitude, like changing nearly the equilibrium field strength, or if it's very weak. Because I think there's no color bus beams, so I'm just wondering what are the disturbances in these models. So.
Yes, I totally forgot to put color bars here in these blocks, but we didn't have the amplitudes of these waves traveling in these.
So I think your source was like 1% of the strength of the field strength. I think the pressure pulse as a source for generating the waves was about 1%. So that I was just wondering how much gets converted and how much is going to change.
Okay, but
and then the final question is: do you have any idea now how or what could be the trigger? But you said you put like the pressure pulse next to the flux tube in a certain depth. That's your association. But any idea what could create this pressure pulse there in this depth? Because I mean that's the next exciting question.
Yeah,
of course. You showed very nicely that next to the flux tube, if you have this pressure pulse, you can cause all these acoustic waves and explain it. But so of course, the following question is then what could cause these pressure pulses?
Well, there are regions in the interior of the sun, which after as well, I'm gonna go to this slide here, showing this behavior located well, actually located there. Sorry. Yes, for example, these energy sources are coming. We think of in this way: if in the outer regions of the solar atmosphere there's magnetic energy stored, by the action of these charged particles around these magnetic field lines, and then after there is some change in geometry of these magnetic tubes in the outer atmosphere. So this has the capability of make a conversion between this magnetic energy into kinetic and thermal energy. We think that it might be also possible that in regions beneath the solar surface, the magnetic field coming out from an active region to the exterior of the sun and then to the interior. These magnetic fields also have a certain extension in depth beneath the solar structure. So we think, okay, there might be also encompassed magnetic free energy in order to be converted to these.
And you're thinking of something maybe like a magnetic reconnection happening subsurface in as a consequence of the trade-off. Or maybe it's the particles, several the particles which come down and hit the atmosphere and create some pressure.
Well, we think of this solar element to be like a trigger for like this stabilization of the magnetic field structure in the solar interior in order to give rise to those acoustic observations.
Okay, and I have a last very naive question for a person who is not into something. So did you do the code yourself, or this is a code available, and so other people who are interested and want to start working with these focus, defocus techniques and so on, they can download it somewhere and get a manual and get into analyzing the data?
So we use the Pluto code. We started making all these considerations from scratch.
Yeah, that was for the simulations, but I mean from the observations with you are
related to the holographic image?
yes, exactly.
No, we make use of the acoustic holographic method from Charles Lindsay and Dan Brown.
But they had like a fixed software package you can get and start working, or
yes.
you implemented the methods then yourself?
No, actually, we use the code, these computational calculations, to account for these source, for these acoustic maps.
How much computational power?
No,
really good computer, so you can run it.
No, for example, I run all of these observations of the acoustic field in this computer, and it didn't last too long. It's really good for this part.
Okay, I think from my side, that's all. And as I said, I want to contact you. It's very sophisticated work, comprising a lot, like from observations to simulations to interpretation. So I love it. It covers this.
Muchas gracias, profesor. Entonces, para unas preguntas por parte del profesor Santiago.
No sé si hablar en español o en inglés. ¿Qué te gusta? ¿Alguien que prefiere? No. Bueno, en español es fácil para que domine. Pues bueno, coincido con Dominic, un trabajo que me gustó muchísimo, la presentación porque estaba muy bien organizada, responde muchas de las preguntas que tenía al leer el texto. Así que felicitaciones, creo que ha sido un buen resumen que muestra efectivamente un trabajo importante, intenso, muy pertinente y con muchos aspectos diversos, ¿no? Tanto la parte de análisis de datos, muy bien trabajada, la parte de desarrollo de código, utilización de código que ya existe, mejoramiento, y luego la parte complementaria de la simulación, que me parece que pues, también hace que el trabajo sea muy robusto, ¿no? El objetivo de la maestría como tal siempre ha sido pues, formar al estudiante en investigación y hay muchas formas de hacerlo. Y me parece que en este trabajo se condensan muy bien muchas partes que nos interesa que los estudiantes dominen, tanto la parte de análisis y procesamiento de datos como la parte de desarrollo numérico. Así que felicitaciones por eso a Ángel y a los supervisores, ¿no? Que es un trabajo consensuado, muy bien planteado. Bueno, tengo algunas preguntas, algunas ya las solucioné con las respuestas que le diste a Dominic. Una muy general tiene que ver con cuáles serían las diferencias esenciales en esta primera parte cuando mencionas los métodos, por ejemplo, diagrama tiempo-distancia, la holografía, cuando se usa una u otra, es decir, son dos métodos alternativos o complementarios.
Sí, pues, por ejemplo, para la observación de estos sombras, también se puede hacer por observación directa, es decir, como por ejemplo tomar diferencias en imágenes de diagramas para mirar cómo se propagan.
O sea, casi que manualmente, ¿no?
Exacto. Esta técnica fue propuesta después, pues para mirar si en esencia había un sismo solar propagándose en alguna región de la región activa. Y ya pues después vino la técnica de holografía acústica, en donde los autores, Charles Lindsay y Dan Brown, ellos dicen, bueno, pues si podemos ver esas consecuencias de ondas viajando en la superficie solar, pues debemos ser capaces de recrear con un modelo en tiempo reverso para recrear las ondas que se originan de una fuente. Entonces, sí, pues serían como métodos complementarios, digamos, en este, que es un método robusto, pues podemos identificar la localización de esas señales que producen esos signos.
De que en últimas este es el que nos daría más información para caracterizar.
Para caracterizar esos signos, sí.
Bueno, ahora en la parte donde muestras el enfoque y desenfoque de las imágenes. Desenfocadas, que son buen día, digamos,
300 por 300 megavatios
sí,
en longitud horizontal.
correcto.
Ya lo que los autores hacen es, ellos colocan para probar esta técnica, eso
Sí, ¿no? O sea, llevándolo al escenario solar, es un valor que comparado, por ejemplo, con la zona convectiva, ¿qué tal?
exactamente. En el paper pues está especificado que ellos habían puesto precisamente esos valores para mirar cómo evoluciona la técnica de holografía y que, por ejemplo, que pupila se debe utilizar.
Estudiar posibles mecanismos de generación de ondas o señales acústicas a diferentes profundidades, ¿cierto?
Sí, señor.
En pocas palabras,
Y con eventos que ocurren en la atmósfera. Lo que nosotros proponemos acá es que estas señales acústicas pueden ser pues de que hay una configuración, hay una parte de la configuración que viaja hacia regiones más bajas de la atmósfera, y esa es la que finalmente origina el trigger más profundo. Entonces, lo que proponemos
A propósito de si puedes poner la imagen, justamente, exacto. Entonces, uno podría pensar ahí, claro, yo tengo el impacto de, o sea, el efecto que dice el sol, y
no, creo que sigo teniendo internet.
no, estamos bien.
Sí, aquí tengo internet.
Y aquí también está todo bien. Bien. Entonces uno podría pensar si esto lo lleváramos a otro escenario muy distinto, pero solo para dar una idea, ¿cuál es el efecto que tiene ese impacto en todos los puntos interverticales? Uno podría pensar, hay innumerables fuentes entre el punto de arriba y el punto de abajo. Entonces, ¿por qué la fuente se considera abajo y cuál es ese caso? No, puntos intermedios es
Consideramos región interior solar. Por ejemplo, en este caso, esta región está localizada en dos diferentes profundidades. Ya lo que hace esa región, lo que se le hace a esa región es que a partir, por ejemplo, de una acción externa, precisamente esa energía se libera, la energía que está almacenada precisamente en estas regiones se libera para generar esas ondas acústicas. Entonces, o sea, que anteriormente se tenía que era directamente, o sea, esos signos era producto directo de impactos debido, ahorita puede ser explicado de acuerdo a las observaciones y a la simulación que se hace a partir de una región que tiene llama almacenada para poder generar esto. Entonces, a partir
diferentes, en la primera parte, diferentes fulguraciones, hay una semi, otra tesis.
sí,
Una pregunta es cómo se escogió esa muestra, si había algún criterio para escoger esa muestra. Y asociado a esa pregunta, ¿qué diferencias esenciales hay entre M y X? Porque no, claro, las detecciones se hacen en N. ¿Hay algo que se pueda concluir en cuál?
bueno, para la primera pregunta, nosotros escogemos estas configuraciones de una muestra, bueno, de dos muestras. Entonces, nosotros escogimos estas configuraciones de manera tal que puedan abarcar un rango más o menos amplio en la clase. espectral de la fulguración y que también estuvieran sísmicamente activas. Ah, bueno, y además que estuvieran en regiones solar que abarcaran más o menos en regiones no tan cerca al limbo solar. Esa es la primera. Y ya pues, para la caracterización de sismos solares diferentes fulguraciones, casi siempre para, o bueno, es muy probable que encontrar sismos solares para fulguraciones de clase M, mientras que no es tan probable encontrarlos para fulguraciones de clase M, pero es debido a que a lo largo del ciclo se X. Entonces es una muestra mucho más grande para encontrar dichos zonas.
Y justamente pensando en los efectos de proyección, ¿cómo se puede hacer?
Serían de óptica geométrica, que son en simples aberraciones, aberraciones 6D, pues se van a ver como más, si ser mucho más difíciles de corregir.
Y a propósito de errores, ¿qué errores están aquí involucrados? Porque por ejemplo, el valor que da
Es más o menos
para saber que son 10, pero no exactamente 10, sino. Es decir, ¿qué errores podrían estar ahí? Implicando que esa frecuencia no sea
temporal, pues ya se tiene que mirar es, pues precisamente la parte temporal de estas observaciones. De lo que pensé en antes. Es un valor fijo acá, la homología asociada a esas fuentes, pues ya se tiene un límite de difracción. Entonces, en el cual pues, miramos cuál es el límite de difracción, pues para poder discriminar esas.
perfecto. Y si tuviera, ¿qué sería el valor límite de frecuencia que podríamos analizar con la mejor cadencia de polígono?
Si, por ejemplo, si si viene un instrumento que tenga una cadencia, en este caso el doble, para las observaciones, porque sería una cadencia dos veces. No la tengo acá, pero hay una fórmula para calcular la energía asociada a estas configuraciones que depende también pues de las lecturas de estos mapas, de estos mapas de dirección acústica y también como función de la edición. Hay precisamente una forma de calcular esas energías, como por ejemplo, se evidencia que ellos utilizaron un método similar. De hecho, ellos utilizaron el mismo método de holografía acústica y ellos dieron cuenta de esta distribución de energías, precisamente calculándola con esa forma.
Luego pregunta así, cortitas, ¿cómo se selecciona el tamaño de la pupila? ¿Hay un criterio, aparte del criterio visual?
Sí, por ejemplo, bueno, me voy a volver un poquito hasta acá. Si queremos ver una fuente acústica que está a cierta profundidad con respecto a la fotosfera, entonces el tamaño de la pupila, el radio interior de la pupila, debe ser más grande que ese tamaño. Eso es para evitar, pues, porque lo que sucede aquí es que tenemos una fuente, por ejemplo, esta fuente.
Pero el tamaño de la fuente es como el kernel que nos saca del programa.
El tamaño de la fuente es más o menos el que nos está indicando la técnica de holografía. Entonces, por ejemplo, esta fuente emite pues, ondas en todas las direcciones. Particularmente hay una región en la cual esas ondas viajan directamente hacia arriba y son leídas en la superficie. De hecho, aquí en la técnica de holografía hay como dos, que se llaman como observatorios. Uno que es un observatorio subyacente y el otro subyacente. Aquí en el subyacente, en principio analizaríamos únicamente imágenes alrededor de esta región. Es decir, que la pupila en realidad sería un círculo con un radio más o menos de esta forma, más o menos un radio de este valor, sin pues este anillito ahí adentro. Esto sería con el observatorio subyacente, pero aquí, como analizamos fuentes a cierta profundidad, pues vemos las fuentes de onda, los frentes de onda que viajan e impactan en la superficie. Entonces nosotros que decimos, bueno, pues que el radio interior de la pupila sea más grande que la profundidad a la cual estamos haciendo los cómputos de holografía acústica. Y ya pues para este radio, bueno, pues también seleccionamos un radio amplio, debido a que precisamente si tenemos fuentes más sumergidas de lo normal, pues naturalmente sus ondas van a viajar más en profundidad en el Sol y pues van a pegar aquí en la superficie a un radio mucho más grande.
O sea que en ese sentido, entre más grande sea el radio, mejor, porque estarían excluyendo
pues,
los efectos más.
Pues digamos que en principio pues sí, porque consideraríamos ondas que están viajando muy al interior del Sol y refractadas hacia la superficie. Pero como esta técnica es esencialmente óptica que aplicada en el caso mecánico, en el caso acústico, pues también heredamos ciertos problemas respecto a la geometría. Si seleccionamos una pupila de un radio externo más grande, pues vamos a tener, por ejemplo, más problemas como aberraciones esféricas del mar. O, por ejemplo, algunos problemas como relacionados también, por ejemplo, con el astigmatismo, en el análogo, y otras, como por ejemplo también, bueno, hay varias, que son las aberraciones de CD. Entonces, entre más grande es este radio, pues mejor para estas ondas, pero pues también va a ser un poco menos bueno.
Va a introducir más fuentes de error también.
Exacto. Para las fuentes, pues van a introducir, sí, van a introducir eso.
Perfecto.
Ese error.
Sí, lo estaba pensando porque, claro, esto si uno lo quisiera hacer de manera 100% automática, pues tendría que crear un algoritmo que tuviera una especificidad para cada región. Es decir, no se puede plantear un solo una sola serie de parámetros para todo. Ya.
Sí, no, de hecho, lo que ellos hacen acá es jugar con diferentes pupilas. Y lo que hacen es jugar con diferentes pupilas, pues para recrear de una mejor manera las fuentes acústicas. Entonces dicen, ok, esta, por ejemplo, es un observatorio, esta es otra, esta es un conjunto, la agrupación de esos dos observatorios, así.
Bueno, ahora ya unas muy cortitas, diapositiva 19, por favor. 19. Ese QS de arriba a la izquierda, que es de la escala.
Intensidad normalizada.
Okay.
Sí, es intensidad normalizada.
Al quiet zone.
Sí,
pues
sí.
quiet zone. Okay. Perfecto. Y en la 20. Bueno, aquí un comentario que tengo es que el C no existe, ¿no? O sea, es que cada kilómetros S para denominar los
Sí, profe, sí, señores.
Vale,
Es eso.
Sí, una tontería, pero pues, bueno. Sí, exacto, sí. Y en la 28, me quedó la duda sobre los tiempos, esa secuencia temporal. Los dos últimos son el mismo, ¿no?
Bueno, aquí no miro secuencia temporal, aquí solo miro el mapa de digresión acústica entre 9 y 11 MHz.
De acuerdo.
Y cómo varía como función de la profundidad. De hecho, aquí pues te muestra que a la derecha, en la parte de arriba, en barras y números, la profundidad a la cual se está realizando el cómputo de holografía acústica.
De acuerdo. O sea, ahí en los dos últimos son simultáneos.
Sí, pero aquí están.
Sí. Bueno, no, yo no quiero extenderme más. Pues vuelvo a repetir que este trabajo creo que abre una línea importante dentro del grupo. Así que felicitaciones por eso y gracias también por eso, porque hay unas perspectivas muy buenas de seguir aplicando esto y que nuevos estudiantes puedan retomar todo esto que se ha hecho y seguir profundizando en esa dirección. Entonces, en cuanto a eso, esa última pregunta es, ¿qué tan fácil es, por ejemplo, que esto pueda tomar un nuevo estudiante que esté interesado en seguir en esta dirección?
No, pues el estudiante puede pues, solicitar los códigos para hacer estos cómputos de holografía acústica y incluso hacerlos el mismo, seleccionar las pupilas adecuadas para mirar con la técnica de enfoque la profundidad a la cual las fuentes están localizadas. Entonces, sí, yo diría que es relativamente fácil retomar el trabajo por un estudiante.
Bueno, Ángel, felicitaciones por mi parte.
Gracias por la
Bueno, gracias por el trabajo. Ahora entonces podemos dar un paso de preguntas por parte del público. No, nada de. Digamos, las notas se producen porque hay un flare que choca contra la. Pero se pueden dar el caso, no sé si de dos y que se da la superposición de las ondas.
Sí, pues sí, de hecho, la técnica de holografía, bueno, lo que se pensaba era que había un choque fotosférico que produce las ondas. Y pues, sin embargo, planteamos ese nuevo método, esa nueva hipótesis que está relacionada con la generación de esas ondas. Pero, en principio, bueno, para esta columna.
Ángel, pero si tiene el audio ahí ya.
Sí, profe. En principio, la técnica de holografía también se ocupa si tenemos varias fuentes. Por ejemplo, acá tenemos dos fuentes en el interior solar. Cada una de estas fuentes produce esas señales que se ven en la superficie, como esas ondas que se propagan. Y sí, lo que hace la holografía es leer la información como función del tiempo de esta superficie y hacer un modelo que propague esas ondas atrás en el tiempo, de acuerdo a un modelo solar estándar, pues para mirar si ciertas ondas fueron generadas por una fuente o no. Entonces, por ejemplo, acá si tenemos superposición de ondas, pues igual se calcula igual se calcula los mapas acústicos en diferentes profundidades y pues se puede ver si parte de luces de ondas fueron generadas por una fuente o no. Digamos, si nos vamos acá hacemos cálculos más profundos, pues podríamos ver una imagen más, más definida de esta fuente, que daría cuenta de estas ondas.
Listo, para finalizar entonces vamos a dar la palabra al director y el gerente del proyecto.
Muchas gracias. Bueno, primero que todo, quiero felicitarnos a Ángel porque usted una vez recibió, digamos, ese trabajo casi como misión. Lo llevó a cabo con todo el entusiasmo y el trabajo que han visto. Y es así como pues ahora nos puedes presentar estos resultados, que además tiene un antecedente en la publicación de Sustentación, ahora en ese proceso debo también reconocer y agradecer al doctor Juan Carlos Martínez, de parte esencial, que nos ha acompañado en varios procesos. En este caso particular, pues, también muchas otras personas que intervienen, como el doctor Juan Camilo Ultrado. Y al doctor Charles, quienes en este proceso de formación también nos acompañan en este proceso. Así que, ¿no? También por felicitarlos, porque creo que es un trabajo de
No sé si el profesor Juan Carlos Martínez tiene algunas palabras.
¿Tengo que decir algo?
Creo que mutó este.
Si quieres, pongo la audio ya.
Pongo el audio acá.
Sí, sí.
Listo, creo que ahí ya se escucha, ¿cierto?
Entonces, yo lo único que puedo decir es de que...
Ahora sí, ya se escucha.
Listo. Entonces, lo único que puedo decir es de que ha sido un placer trabajar con usted, Ángel. Su trabajo realmente ha sido muy bueno. El resultado de que sean 2 artículos y que esto vaya a ser como una nueva herramienta de trabajo en el estudio de la diosismología es muy importante y espero que lo continúe haciendo.
Así es.
Listo. Felicitaciones.
Entonces, pues nada, Ángel, pues felicitaciones. Vamos ahora con los dos jurados para ver si se toma la música de la tesis. Entonces,
Entonces,